Okay, well, let's go over the first model function then. I'm going to start here with the um, derivative graph problems. So this category or this model is named that way because you usually are given the graph of a derivative of a function. And then usually you have specific area sections that are identified in the graph. So you have the values of the areas. You usually have given certain points like this here and this here, and you can read the x-intercepts from the graph. You can read the y-intercept. You also have this given here. So there are usually ways to identify certain values, and you can read the second derivative just by identifying where it's negative, where it's horizontal, and where it's positive. So these are the things that are given. Another piece of information that is always given in this type of problem is one point that I'm calling an anchor point. That is on f of x, you have one specific point given that relates the x input to the actual value of the function. And that is just to give you, the specific antiderivative, quote unquote, to this derivative that is so that it's anchored. So you have a specific function and not just, an antiderivative plus c. So essentially this marks the specific function. And so with that in mind, so in this particular case, we have f of 8. So we know that f of 8 is back here. So f of 8 is equal to 4. And we'll see when we have questions here that ask for specific values on the original function, we have to use that and then just count the values of the areas in the correct orientation, depending on which point is given. So from this point that is given and the areas being given, I can find my way to any value of f of x on the specific graph. So always look for that specific anchor point that is given, and don't overlook that in the information of the problem itself. All right, so the typical formulation here is this is the function graph of f prime of x, the derivative of a twice differentiable function on a closed interval from 0 to 8. Then it explicitly shows you, it tells you where horizontal tangent lines are so that we're not confused about this. So there's one here, there's one here, there's one here. 1, 3, and 5. The areas of the regions between the graph and axis are labeled. So this is what the area values are. And then f is defined for all real numbers and satisfies this specific, you could call this also an initial condition, right? Or an anchor point, as I call it. Okay, so let's go through the points. And the reason why I'm calling this model function or model problem is because these types of questions are always structured in a very similar way. They're always asking very similar things about the information that you can gather from what's given with this with this model. Okay, so find all values of x on the open interval for which the function has a local minimum. A local minimum. So local minimum, you want to first write and remember what that entails. For a local minimum of f, we have to have f prime has to be 0. So f prime of x is going to be 0. And f double prime has to be greater than 0 so that it's concave up. Okay, concave up means it's greater than 0. And that way you would find a local minimum, right? Concave up means the point here at which the prime is 0, the tangent line is horizontal, is going to be at a low point of the concavity. So that's going to be the local minimum right here. All right, so let's find it. So the candidates for f prime of x equals 0 are 1, 3, and 5 as given here in the problem and also in the graph. And now we just have to see where f double prime is greater than 0 at these places here. So right here, it's not greater than 0 because it goes down and then it goes up right here at the point. So that's not a candidate for a local minimum. Here, it's the slope of f prime is negative, so f double prime is negative right here at this point. So not a candidate for a local minimum. And this one here has a positive slope. So this one is the only candidate. So f of 3 is the only candidate for local minimum. Because f prime of x is equal to 0 and f double prime of x is greater than 0. And that's the only point where that applies. Let's go to B, determine the absolute minimum. So absolute minimum, you have to take into account the local minimum that you found here and the endpoints. So we want to know the values of f of 0, f of 3, and f of 8. Oh, I wrote this the wrong way, right? So this here is f of 3. I was actually talking about f of 5, but then I wrote it wrong here. So let's fix this. This is actually 5. 5 and 5. And then we also want to find f of 8. And we're finding these by counting the areas from the specific values. So from the specific value given. So we're going to have f of 0 is equal to f of 8, which is given, so that's 4. And then we're going to say plus the integral from 8 to 0 of f prime of x dx. 8 to 0, okay? Okay, so that is the formula for it. And then you can just count it from here. So it's 4. Let's move these out of the way. And maybe we can just make a stop over here at 5. So because this here is 4 plus integral from 8 to 5 of f prime of x dx. Okay, like so. Actually, let's move this whole thing over this way a little bit. That way I may be able to fit it in. Okay, so f of 8 is obviously 4. That's the easy part. Now f of 5 going back from 4. So the area is above the x-axis. So moving in the opposite direction is going to make this negative. So this here is going to be 4 minus 7. And that's equal to negative 3. So that's lower than the endpoint. And then this here is equal to 4 minus 7. And then let's see, this area here is below the x-axis, but we're moving through it in the opposite direction, in the negative direction. So it's negative times negative, so that's actually positive 3. Then we have an area here that is a negative area, so it's minus 6. And then this area here is negative as well, so minus 2. Okay, and what is this altogether? This is negative 3, this is 0, negative 6, negative 8, negative 8. So the absolute minimum is at f of 0, which is the starting point, okay? And that is equal to 8. All right, scroll up here and go to number C. On what open intervals contained in 0 to 8 is the graph of x both concave down and increasing? Okay, so here the condition that we're looking for is increasing, that means f prime is greater than 0, and concave down, that means f double prime of x is less than 0. Concave down, down, and this means increasing. Okay, so now we're just going to look at the graph and read where is f prime, the function itself, here the function that we're reading, f prime, where is this positive? And so that is the case. First case here is from 0 to 1, 0, 1, from 1 to, what is this here? 3, 1, 2, 3, 4. That's actually 4. Gosh, look at this. I have to revise all this stuff here because it's not 5. These were the values for horizontal tangent lines, okay? But the calculations are all correct, just not the point here. So the local minimum is actually at f of 6. And then here we have to find f of 6. But these numbers here in the calculation were also already correct. All right. Okay. So here it's from 1 to 1, 2, 3, 4. Then it goes negative here. So from 1 to 4. And then it comes back up 5, 6, from 6 to 8. From 6 to 8. So these are the sections where it's increasing. And then let's read the slope from this graph here. And we're looking for negative slope. So the slope is negative from 0 to 1. Okay, this one is negative from 0 to 1. Slope is then positive here. Now here, from 3 to 5, it's negative. So 3 to 5. And that's all. Then the rest of it is positive. So that's all there is for negative slope. Concave down, negative slope of that. So now we have to find the sections in the domain here that are overlapping between this, because we need f prime to be greater than 0, which is the case in all these snippets here, and then f prime of f double prime of x needs to be negative. That's the case here. So the overlapping segments are 0, 1, and let's see here, that is 3 to 4, right? Yeah, 3 to 4. Okay, so this is the answer. The reason is because on these sections, f prime of x is greater than 0, which means f is increasing, and f double prime of x is less than 0, which means it's concave down on these two sections. Open intervals. Okay, that's C. Now let's go to D. Might need a new page for that again. Let's see, that might not be enough there. So here we go. The function g is defined by g of x. Let me write this here real quick. G of x is equal to f of x cubed if f of 3 is negative 5 over 2. F of 3 is negative 5 over 2. Find the slope of the line tangent to the graph of g at x equals 3. So in this case, if we're looking for the slope of g at x equals 3, we have to find g prime of x. And we have to use the chain rule to differentiate this thing here. So we're going to have 3 f of x squared, and then multiply this by the derivative of the inside, and that is f prime of x. Okay, that is g prime of x. And now what else are we given here? We're given f of 3, so that goes on the inside here. Let's plug this all in now. So g prime of 3 equals 3 times negative 5 over 2 squared times f prime of x. And f prime of x is still going to be here in the graph. So f prime of 3 is, you just read the value here, is 4. Okay, times 4 on this one. And that value then is 3 times negative squared becomes positive, so I don't have to worry about the negative sign here. And that is 25 over 4 times 4. These 4s cancel. So I have 3 times 25. That is 75. And that is the answer. Oops, too low here. This looks like a square root now. Let's see. Anyway, that's the answer. Okay, there you go. That's the model. Let's double check if we're right. The answers are right here. X equals 6 is the only critical point at which f prime of x changes sign from negative to positive. Therefore, f has a local minimum at x equals 6. From part A, the absolute minimum occurs either at x equals 6 or at an endpoint. We're checking, we have the formula of the integral here. That's important. And we put the numbers together like this and find that f of 8 is equal to 4. Oh, no, that's the given part. So we have here the computations. So f of 8 is 4, f of 0 is negative 8, f of 6 is negative 3, and the absolute minimum on the closed interval is negative 8. And that's at f of 0. So we got that right. The graph of f is concave down or increasing on 0, x between 0 and 1, and x between 3 and 4. We have that as well right here, because f prime is decreasing and positive on these intervals. All right. And this one here, we have the answer right, and we have g prime of x. The formula here is identified correctly, and then just insert the values that gives us the answer. So there you go. That's the model. And I make this this document available to you with the answer keys printed, and you can see here are the other types of questions. I think they're like 4 or 5 of each of these in the model thing here, and you can always see, where they were actually given. Okay, that's it for this video.